intervals. Okay, I'm going to start with a review of sampling distributions because confidence intervals are strictly related to sampling distributions, and I'll try and make that connection clear between them and talk about what confidence intervals are and how to construct them for a population mean or proportion, and go over some results from the survey. Yes, all right, class time. Okay, here are the learning objectives. I'm going to skip through some of this stuff in the interest of time. If I can. Okay, I talked a lot in previous classes and hit some questions on the exam about the difference between a population and a sample. This is going to continue being important, and it seems kind of clear when you look at a picture like this what the difference is, but I assure you that once you start getting into the nitty-gritty of doing these tests, a lot of you are going to forget which it is you're talking about. So I just want to emphasize this and keep everyone thinking about whenever you're answering a problem, are you thinking about the population or the sample? And again, the population has to do with individuals, and it's a large group of individuals. We're not going to observe them all. And the sample are groups of individuals. So when we talk about a sampling distribution, we're talking about the distribution of average properties of these groups. So if you take a bunch of groups or samples, it's the property of the averages of those groups. It's no longer about the individuals. It's about the averages of a bunch of individuals. And in most of statistics, we use properties of that group and its average to make inference about the entire population. Oops, I just skipped to the very end. Okay, and a reminder of some notation. Are we missing? Okay. Again, we're using Greek letters generally for the population parameters and English letters for the sample statistics, but I added to this an exception to that, talking about proportions. For proportions, we'll use capital letters for the population and lowercase letters for the sample. Okay. So you remember that the sampling distribution, so the distribution of the means, is different from the population distribution, and always the variance of the sampling distribution is less than the variance of the population distribution, except in the case of n equal to 1, then it's the same thing. But anytime n is larger than 1, it looks like this, and your variability in the sampling distribution is less. And the larger n is, the less variability there is in the sampling distribution. And you can think of that as, you know, the more people you look at, the less variability there is in their average properties. And the central limit theorem was all about that, the relationship between the population distribution and the sampling distribution. And the important parts of that were that the mean of the two distributions are identical. So that's going to be very important. So the value that you expect on average for the sampling distribution is the same as for the population distribution. Okay, that's the only thing that is necessarily the same. The variance is different, the shape of the distribution might be different, but the mean value is the same. So that will be critical for what we're doing today. And the other critical part for what we're doing today is this relationship between the standard deviation of the population and of the sampling distribution. And they're related by this. the standard error, which is the standard deviation of the sampling distribution, is the standard deviation of the population divided by the square root of n. So remember that. I'm only going over again the things that are important and that we're going to be using again. This is just a review here of standard error, and as I was saying, the larger n gets, the less variable this sampling distribution gets. And that's going to come into play today, because when you build a confidence interval, the larger a sample size you have, the narrower your confidence interval is going to get. And that is because of this property of the sampling distribution and because of that relationship between the standard error and the standard deviation. Okay, so given the mean and the standard deviation of the population, and given a large enough sample size, we can say exactly what the distribution of the samples is. So it's got the mean that's the same and the standard error that is sigma over square root of n. And that's, so any questions now about the central limit theorem, about sampling distributions and their relationship to the population distribution? So after this, we go on to confidence intervals, and it's going to be based on this. I don't see any questions. So confidence intervals. And this is our first estimation problem that we're doing in this class, and the rest of the class basically is going to be estimation. Yes, question. Yeah. Yeah. That's right. That's it. It tells you what your sampling distribution is. It tells you what the mean is, it tells you what its standard error is, and it tells you that it's normally distributed as long as n is large enough. That's all the central limit theorem is. You're welcome. Okay, so a point estimate is something that you're familiar with. A point estimate is your best guess at something. So if you're guessing someone's age, that's the age you guess. So you think it's the most probable value. So, you know, on the age line, you just pick one of these values. But that doesn't tell you anything about sort of how uncertain you are in that. You could put a probability just on that one estimate. But the other thing that you might do, which is what we're covering, is you might want to give an interval estimate on it. So give a range of ages here, in which you have a certain confidence. And this is what I was getting you to do in the survey, to try and start thinking about the relationship between a point guess at something, an interval estimate, and how that interval changes depending on how confident you are in the right answer. So the thing to keep in mind about this is the thing that we're going after, in this case the age. It's going to be other things like blood pressure, like whether the proportion of people who die due to some disease. It's a fixed thing, but we don't know what the answer is. So in this case, you know, my age, it's fixed. I know exactly how old I am, but you don't necessarily. So this is all just about the uncertainty in your knowledge of something that is fixed. It's not that thing that is varying or that is uncertain. Is that a distinction that makes sense? Okay. So as of a little bit before class, here were the responses that we had so far to the survey. I just went and plotted them. I hope you can see them all right here. There were 12 responses so far. And so what I did is I sorted them from lowest to highest based on the point guess, the single age year, and that I plotted as a round dot, and then I put in dashes the 50% confidence interval, and in solid lines the 90% confidence interval. So just to remind you what this was asking for, the 50% confidence interval, that was an interval in which you should, if you were a betting person, be willing to bet even money. So there's a 50% chance you're right, that it is in that range, and a 50% chance you're wrong. And then the 90% confidence interval was something that you're more confident in which you're 90% confident you're right. Or if you were a betting person, you would bet someone $9 against their $1 that you're right. So you want to be quite confident. So given those definitions, I want to ask you to take a look at these and tell me which of them make sense and which of them don't. Just look at them one by one and tell me if you see any there that don't make sense. Yeah. Yeah, so number 4. This one I don't think makes yeah. Okay, well, another question? Okay, let me talk about this one and then we'll go with a different one. So number 4 here, the best guess is at 34, but the 50% confidence interval is at 25 to 30. So I would ask there, if this is your best guess, then why isn't the interval in there? And there are unusual cases where maybe that could happen, but generally your confidence interval should include your best guess. Is there another one? Were you going to ask about another one of these? There are some other ones here that I think. Right here? Yeah, you're right. What, you want to tell me why? Yeah. Yeah, the 90% confidence interval is narrow and the 50% one is wide. So it's saying you're very confident that it's between 35 and 37, but less confident that it's between 32 and 42. So I think that one just got switched around. But that's a key concept, and something that's going to come up in how we ask you to interpret these things, which is if you want to be more confident, then the interval has to be larger, right? So, you know, take another example. If I asked you, you know, in what year was Lincoln born? If you don't know and I say you'd better be right in this interval, you're going to give a huge range. You're going to say maybe from like 1000 BC to 1999 if your life depends on it, right? Okay, so just remember that the more confident you want to be, the bigger the confidence interval has to be. Oh yeah, and one other question. So another thing you'll notice about these is that some of them, so here's one that I think makes perfect sense. There's one thing I notice about it which makes sense to me is that the point estimate is right in the middle of the interval. You know, that wouldn't always be the case. Like if you had some reason to know that it was impossible, that I was not younger than some age, then maybe it would extend further on one side. But probably most of the time, the point estimate is going to be in the middle. And here we have a 50% confidence interval and then a 90% interval that's about twice as big. All of this makes sense. What would you say about this person, number 5, in relation to number 10 here? Which one is more confident about how old I am? Yeah, number 10. So you can go the other way too and say if you have a smaller confidence interval, well, they're both 90% confident. It's just that this one has better information, or at least thinks they do, or has a more accurate measurement of the age. Don't worry, we'll get to the answer later. But first, I'm going to tell you how to construct a confidence interval. So in this survey, I just had you construct the interval based on your prior knowledge and your best guess. And I think it's a good exercise to do, and it would be a good one for you to, if you're trying to get the hang of this, to try on various things, to think about what your confidence interval at various levels would be, about how long it's going to be until the bus comes, or what time PH750 class is going to start, to get used to it. But in this class in statistics and in the literature, the way it is generally done is from a sample. So from a set of measurements out of a population. That's what we're going to use to construct the confidence interval. So the way you do it, you take your sample, you have some number of measurements, you have 100 measurements. Yes, question?
I was wondering, why did you use this form of plotting? Could you use another form like the histogram or plot the age in order to calculate the?
Oh, yeah, good question. Why did I do this? I'll tell you, this is a much more complicated plot to make than a histogram, and I don't expect you to be able to make a plot like this. I had to type about 10 lines of code in R to make this plot. The reason is because this is a very informative plot for this very special circumstance. It is showing you each one of the point estimates and also 2 different confidence intervals. So you just couldn't do that in a histogram. Like I could have shown you the point estimates in a histogram, but I couldn't have shown you also each of those associated confidence intervals. I could have shown you a bar plot, I suppose, but then putting 2 different error bars on it would be difficult and would be basically exactly what this is if I just put a bar up to here and then had these 2 as error bars. But yeah, this is not a normal plot. This is just a special plot that I made just for you. So that's why. Okay. So all that is involved in constructing a confidence interval is to take your sample. So this might be 100 measurements of weights, of blood cholesterol, or guesses of someone's age. And you calculate what the sampling distribution for a sample of that size is. Okay? So the sampling distribution is defined. You know that it's well, in the large sample limit, it's normal, and that's what we're going to be talking about today. So you know it's normal. And all you need to fully define a normal distribution is the mean and the standard deviation, which in this case is the standard error. So you get a point estimate from your data, and you get a so-called margin of error. And I'll tell you how to calculate those. But essentially, just to give you an intuitive idea of what it means, this is your sampling distribution. You're just going to take the area in the middle that accounts for whatever confidence you want. So if you want so this is going, if you want a 95% confidence interval, this is what it's going to look like. It's going to be between about -2 and 2 standard deviations. So all of that probability stuff that we had you doing, just calculating probability using tables of the normal distribution or using the calculator Excel is for a reason, because now you're going to be able to use that to calculate confidence intervals. By the way, this website I just discovered, it's linked to in the notes. It's great. It's a little applet for the normal distribution, and it's really nice because it allows you both to calculate the area either above or below, between or outside set values on a normal distribution, and it can either be the standard normal, or it can be, you can specify the mean and standard deviation, and you can also say what the area is, so the probability, and select one of these and it'll give you what the values on here need to be. But the thing that I think is great about it is that it always shows you this plot. So I think you should get in the habit of, whenever you're doing these problems, you know, when you're practicing, use this applet if you need to, but always think about this curve, because this will make sure you understand what you're doing. If you understand which part of the distribution you're calculating the probability for. For confidence intervals, it's going to be the middle section like this. When we go to hypothesis testing, we're going to be calculating the area just in the tails. If we'll do one-sided tests, that'll be one tail. Two-sided tests will be both tails. But if you're thinking about what the distribution is, it's going to be a sampling distribution, and what the part of the distribution is that you're calculating, then you'll understand what you're doing, and you'll do it right. Even if you're using the software to do it, so that you're not actually using a table or anything like this and just getting an answer from SPSS, doing this will still help you to make sure that you're understanding, or drawing this out or thinking about it in your head will help you avoid mistakes. And sorry, I just realized I've gotten behind on questions. But anyways, that's a good website. You should try it. I'm going to quickly go back and answer a couple of these questions. So the question was, anywhere the 50% confidence is smaller than the 90%. There were some there, but there shouldn't be. Or sorry, yes, of course, I'm getting mixed up, but your 50% confidence interval can be smaller than your 90% confidence interval, and it should be. And we will get to my age. Okay. Okay. So this term that I mentioned, the margin of error, so this is how far above and below the sample mean that our confidence interval extends to. Okay? Now, it is going to be a function of the standard error and how confident we want to be, what our confidence level is. So the standard error tells us the shape of this curve, and the amount, our confidence level, tells us what amount of area we want to be contained in this confidence interval. So in the example of 95% confidence interval, which is the one that people usually use, you'll usually, when you read a paper or read about a poll in the newspaper, it will usually be a 95% confidence interval that they're reporting, but not always, and you'll be able to calculate different ones as well. But for a 95% confidence interval, you remember that for a normal distribution, from the empirical rule, 95% is within about plus or minus 2 standard deviations, or 1.96 to be exact. So that's all there is to it for the 95% confidence interval, is to take the mean plus or minus 1.96 standard errors. And this 1.96 standard errors is your so-called margin of error. Nothing too mysterious, right? Any questions about that? Because this is a big step. We're going. This is your first bit of estimation in this class. So if it's seeming kind of, if it's seeming straightforward, that is great, and hopefully I'll be able to keep it that way. It's not mysterious. It's just it reflects your uncertainty in the sampling distribution, because you just have one observation from your sampling distribution. So when we looked, I'm just going to talk about this a little more. When we looked at first at population distributions, we had a fixed mu, a fixed population mean right in the center of it. That's not the case anymore. The center of this is our, this is a sampling distribution. So what we are getting is just one measurement out of this. We don't have all of these measurements. So instead of having that kind of fixed mu with the truth in the middle and looking at the variability on either side, we have an estimate, an uncertain estimate in the middle. That's our best estimate, but it is uncertain because we just have one sample. And so when we calculate this plus or minus 2 standard deviations, this is telling us where that truth might lie, or that's a bad way to say it, but where that true mean may be. So instead of thinking about the truth in the center and all of the variability being around it, now it's our observation in the center and the truth somewhere around, distributed around what we observed. So it's a conceptual thing, but the formula is it's exactly the same. It's just this, you can think of it and plot it in exactly the same way. Are there any questions about what I mean by that? Yes, question. Sorry? Oh, so what is my estimation of the confidence interval based on? It is based on where's my cursor? It's based on the sampling distribution and which range of between which negative and positive value that certain confidence, that amount of probability lies. Right. No, it's not a wild guess at all. It's based on data, and given a sample, there is an exact calculation of the confidence interval. So yeah, whereas when we're guessing ages, we're just that's kind of to get the hang of what the confidence interval means. But this is a calculation based on data, and it's just based on a bunch of point estimates. So what I'm going to do later is take all of the point estimate guesses for my age that I got and use that to calculate the confidence intervals. That's all I need. I don't even need the intervals that everyone gave. If I just treat everyone who responded to the survey as an equal guesser, like an instrument that has some uncertainty in it, then I can use those guesses to get a confidence interval. Another question.
Would it be okay to say
So the sampling distribution of the means is not skewed. There are other sampling distributions that are skewed. We'll get to, for example, the F distribution, which is skewed. But as long as we're just talking about means and about proportions, it's symmetric. But we won't calculate. I don't think anyone uses skewed distributions to calculate the confidence interval. Well, we're taking a data set, which is a set of observations, a sample, and we're using the mean and the standard error of that sample to create the confidence interval. So it's a calculation. You calculate the mean, you calculate the standard error, you go for the 95% confidence interval, you go plus or minus 1.96 times that standard error, and that gives you your confidence interval. So there's no guessing involved in doing that. Yes? But what if it's like very different, like the mean of your sample? So there are two ways that your sample mean could end up different from your pop. So the question is, what if your sample mean turns out very different from your population mean? And it's a very insightful question. There are two ways that happens. One, it can be due to bias. For example, bias in your sampling, or bias in your guessing because maybe I'm older than I look. That is one way that your sample mean can end up very different. The other way, and that, by the way, generally we can't do anything about as biostatisticians. That can only come from sampling design, things like that. When you come down to analyzing the data, there's nothing you can do about that generally. The other reason is just by chance. You just get very unlucky, and you are measuring height in a population, and in your sample, everyone you get is 6'6", just because it was a really unlucky day. That we can account for. As long as it didn't happen because of a non-random sample, as long as it just happened by chance, that is what we're accounting for. We're finding out how much your sample could be off, your sample mean could be off from the population mean just due to chance. So let me see, do I have any? Okay. Okay, so a little bit more to try and build your intuition of confidence intervals. What they do not do, a 95% confidence interval does not imply that 95% of the population values lie between these limits. Is that like abundantly clear to you? I want eventually for that to be really obvious that that is not what a confidence interval is about. And actually, that's a common misinterpretation of the confidence interval. So if your confidence interval is on the average height of North American men, you might be able to, if you have a large sample, to say that it's between 5'10" and 5'10" and 1/8 of an inch. You might be very confident about that average height, and that's what your confidence interval would be about. That does not mean that 95% of North American men have a height between 5'9" and 5'9" and 1/8 of an inch. It is not at all that. So again, it's about the sampling distribution, not the population distribution. That's why I keep on hammering on the difference between those two. And as I mentioned, it does not account for bias. in your point estimate. So we have to assume when we're doing this that the point estimate is an unbiased measurement of the true population value, the true population mean. And that means that, you know, if we're very unlucky and it is quite different, but if we took another sample, we wouldn't be that unlucky again. If we took a bunch of samples, then the average value of them would be the same as the population mean, which is the same way of saying that the sample must be representative of the population in order for this to be an accurate confidence interval. So what it does do is provide that interval in which we have a well-quantified 95% confidence that that true population mean lies. So if you have an unbiased estimator of my age, so if I, you know, look my age, but different people will guess above and below it, then this will give you an accurate interval for if you were going to go and bet on my true age, and when you found out, you would know what the odds are when you go about doing that. And what it does do is if you were to repeat the experiment 20 times, then with the 95% confidence interval, 19 of them would contain the correct value. See what I mean? How it's about just the randomness and just the luck of the draw. So it controls how much luck of the draw can take you off. So, and again, the population value, mu, it's assumed to be fixed but unknown. So it's not, this is not like variability in the population mean. This is our uncertainty in that true fixed value. And keep in mind that mu is not a random variable. It's just a fixed point value. And as I mentioned, if we were to take repeated samples and with every one of them construct a confidence interval, and I have a picture of this here, this is kind of what they would look like. You know, they would vary moving from left to right if this is the true mean and these are the confidence intervals. Some of them would be larger, some of them would be smaller just due to the standard deviation in that sample. But on average, with a bunch of these, 19 out of 20 of them would contain the correct value. And you can imagine how if there were a bias in your sample, all of these would get shifted over so that no longer 19 out of 20 of them would be correct. Of course, if you have exactly 20, then it might not be 19 of them. It might be 18, it might be 20. But if it were like, you know, 20,000 of them, then 19,000 of them, pretty close, would contain the correct population mean. Okay, so I have some questions for you now. First one, so is the 99% confidence interval larger or smaller than the 95%? And feel free to answer online too. Here's one question I'm going to answer. So the 50% confidence interval and the 90% confidence interval has to be the same for everyone for a particular question? No, one of them is going to be bigger. So I want someone else to answer it though. So out of these two, 99 and 95, which one is bigger? 99, very good. So out of the 50% and the 90% confidence interval, which of those should be bigger? Yeah. Okay, so the 90% is bigger than the 50% confidence interval. And as the size of a confidence interval increases, or does the level of confidence increase or decrease? Increases. You guys are doing great. Okay, so for a fixed confidence level, say 95%, as we increase the size of our sample, n, what happens? What's that? It what? Decrease, did you say? Yes, good. Yeah, it decreases. Why is that? If you're thinking about any kind of explanation, why is that? Yeah, so if you have a larger n, you can be more confident in your data. And in terms of the formula, your standard error will decrease. So yeah, the amount of variability that you get between samples is less if they're larger samples. And what does all of this tell us about the variability in the population? This is a trick question here. You're right. It doesn't tell us anything about the population. It only tells us about the population mean, the center, that average value in the population. It doesn't tell you anything about the variability in the population. Okay. Yes.
Maybe I'm thinking of confidence in a different, I'm not thinking of it properly, but the second question is the size of the confidence increase, right? But I guess I think about it like, well, if you're expanding it over a wider range of values, then
Right.
I'm less confident because it's further away.
Right. So the question was as the size of the confidence interval increases, does the confidence increase or decrease? And I said it increases. Maybe what I should have said to be more, to say the confidence level. The confidence level in that estimate, definitely it increases given that nothing else has changed. I think what you're maybe getting at is that if your confidence interval is increasing because you have a less accurate test or a smaller sample size, then it's for a fixed confidence level, your confidence interval will increase, and it's because you have less knowledge, and that's right. So yeah, what I really mean here is that your level of confidence in that confidence interval, given that other things are staying constant, there's like a trade-off there between, if you want to say you have very high confidence, then your guess is more broad. Okay. Any questions from online? I'm sorry that I've been a bit behind on your questions. Oh, people are voting on the answers. That's cool. Yeah, so the larger, that was the 99% confidence interval. It is indeed larger than the 95% confidence interval. So the votes were correct. Okay. Yes, question. Sorry, as you increase what? As n increases, does the 95% confidence interval increase or decrease? The answer there was that it decreases. It gets smaller. Does that make sense? So imagine, okay, it's a 95% confidence interval on the year that I don't know, that Napoleon was born. I have no idea, honestly. So my 95% confidence interval would be huge. And increasing is akin to getting more data, more information. So if someone gave me a hint and said, you know, gave me like the century that it was in, then my confidence interval would decrease. So it means that for a given confidence level, the more information you get, the smaller that interval can be. I have a worked example here. I'm not going to go through it in class, but I encourage you to go through it on your own. I just wanted to point out here in an example of average birth weights. By the way, there is some more in the notes about this terminology, this z underscore alpha over 2. Alpha in this case is the error rate. So for a 95% confidence interval, your error rate is 5%. And this is called z alpha over 2 because if you look this up on the z table, you would look up the z score for, well, if it's a left-tailed thing, it would be minus 0.025. If it's the right tail, it would be plus 0.025. So this is just the value that you would look up. But I think you'll get your chance to practice doing this doing this later. The point is just being able to estimate that central area. But all I wanted to just give you a chance to work out a couple of questions here. The 95% confidence interval, and then seeing as you do it what happens when you quadruple the sample size. So that means that your standard error, which is divided by the square root of n, is divided by 2. So your standard error becomes 0.5 of what it was before. So your confidence in your margin of error gets dropped in half. And then what happens when you calculate a 99% confidence interval? And then you use a different value looked up from the z table, and you get a larger value than you did with the 95% one. Okay, so back to the example of the age. So I went ahead and used just the point estimates, calculated the average of those. So I'm just treating those guesses as a sample from a population, guessing my age. The average age of the guesses was 35.6 years. The standard error was, standard deviation was 3.85. Standard error was 1.1. Now, one thing that I'm not getting in today because I don't want to confuse you with details yet is because not very many of you responded to the survey. It's a small sample. It's n equals 12. So the normal approximation doesn't quite apply. And we're going to get into using the t distribution, the student's t distribution for that case instead of the z distribution. But it's the same thing. It's just the table that you use for looking up those tables, or the function you use will just be, it'll be t instead of norm. So everything is basically the same though, and I show you what difference it makes here. Using z, the 95% or the 50% confidence interval goes from 34.8 to 36.3. And you can see that for the 50% confidence interval, it makes very little difference whether if you use t. And the 90% one, as we expect, it's a wider interval, so it goes all the way down to 33.8 and up to 37.4. One thing you'll notice is that there's a bit more of a difference with the t, and this is why kind of when we give you these rules about n equals 30 and stuff like that, it's a little bit fake because it depends on which part of the distribution you're looking at, and it turns out that the t is more different than the z the further out on the tails that you get. In the central part, they're almost the same. So here is the class's 90% confidence interval. And the answer is I'm 40 years old. So I don't think it's because there's a problem with how confidence intervals are calculated. I take it as a compliment that I look younger than I actually am. Or just that you're being nice to me because I'm your teacher. But that would be an example of bias, and so we can't, you know, this doesn't include the true value because there's a bias, and people tend to guess that I'm younger than I actually am, at least the 12 people who answered the survey. Questions about that? Because we're basically at the end of the lecture here. Yes. Yeah. Right. Yeah. That's because it's a biased. That's because it's a biased sample. So if I were to go and do this next year in class and say, I know that people tend to underestimate my age by 4.5 years and apply that correction to it, then if I do this year after year applying the right bias correction, then I would find that you know 9 classes out of 10 would get me right. But all of this, it cannot account for bias. So that's something to keep in mind when you're reading the public health literature too. When you see that confidence interval, it only works if you have an unbiased sample. Well, some are less biased than others, but yeah, polls, you know, that confidence interval that they give you, it relies on them having got an unbiased sample from the population, or else that confidence interval, you know, it's not as confident as they say it is. Good question. I don't see any online questions. Comments? Why I have to estimate what? Okay. Yeah, so the question was, I have data that tells me a mean and a standard deviation. Why do I have to do this confidence interval estimation? Yeah, good question. And the reason is because that mean and standard deviation that you just get directly from the sample, those would be about an approximation of the population distribution. That standard deviation tells you about variability in the population as best estimated from that sample. So for example, you know, like the example with the height, if I take the height of everyone in this room and I want to know what the average height of Hunter College students is, I can get a fairly accurate estimate of that average height. It's not going to vary very much from class to class, the average height, but individuals will have a lot more variability. So that calculation is about saying it's not the individual variability that we're interested in. We want to calculate something about the average properties like at the average height of Hunter College students. That's why we have to do all this extra stuff. Does that make sense? Because we did in the first classes, we calculated, we gave you a mean and a standard deviation, and we had you calculate the probability that an individual is outside of this limit or between these limits. But all of that just had to do with individuals, and because in public health and other things, we want to know not just about individuals, but about the aggregate properties of groups of people. We have to move to sampling distributions. I'd love it if someone else wanted to answer this question too, for me to hear it in a different way. You'll hear it in a different way from Tony tonight. I think Ali is sick, but that might help, and kind of getting your hands dirty with it a little bit might help as well. So we have, yeah, this is just the wrap-up slide. We've talked about all this. I think I should get you down to the lab now. Any more questions from online? The class is packing up now, but I can stick around for another minute. What's that?